Well, I wanted to take another shot at this video. I put one up very similar, covered very similar topics, but I had so many good questions and comments and things that I should have included in that earlier video and didn't, and things that I put in that earlier video that I shouldn't have, that I thought, well, what the heck, I'll just delete that earlier video and try this again and try to cover up some of the issues that I should have covered in that last video. So we're going to be talking about telescope resolution, but also in the context of the guiding that you're capable of seeing that you have at your location. And there's a couple of limits here that we're used to hearing, and I want to talk about those in particular because they are very important in terms of getting optimum telescope resolution, and that's Dawes Limit and the Nyquist Limit. You've probably heard of those terms before. And they're in a bit of a battle. So in one corner we have Dawes Limit, and the other corner we have Nyquist Limit. Let's see who wins out. I have a Celestron SCT 925, so 235 millimeter aperture, and on Celestron's website it quotes the resolution, the Rayleigh resolution at 0.59 arc seconds and the Dawes resolution at 0.49 arc seconds for this particular scope. Let's take a look at where these numbers come from. The equations are very similar. In the case of the Rayleigh limit, we have a 1.22 times lambda, which is the wavelength, and here I'm using 550 nanometers, which is in the middle of the green area of the spectrum, divided by the aperture of the telescope, which is 235 millimeters. And then this little thing in parentheses over here just converts the angle in radians to arc seconds. And if you plug these two numbers in, making sure to convert this one into millimeters or convert this one into nanometers, whichever one you like, they have to have the same units. But when you plug these numbers in, you compute that the Rayleigh limit is 0.59 arc seconds, which is what is being quoted here on Celestron's website. Meanwhile, the Dawes limit is kind of an empirical formula developed by William Dawes, an astronomer back in the 1800s, I believe. He came up with an empirical relation that characterizes how close two stars can be before you lose sight of the fact that there are two stars there. And he came up with his limit, which it turns out numerically is just extremely close to what we all know as the full width at half maximum. So from now on, I'm going to be using Dawes limit and full width at half maximum interchangeably. And in this case, if you plug in the 550 nanometers for green light and 235 millimeters for the aperture of this particular scope, you'll come out with 0.50 for the full width at half maximum, which is very close to the 0.49 arc seconds that Celestron reports for Dawes limit. Imagine we have two stars. Now, in the case of Dawes limit, what Dawes is saying is if you shifted the second star off from the first star by an amount of full width at half maximum, or Dawes limit, then the two peaks will be separated by the full width at half maximum, and when you add the light from the two stars, you'll see a peak, you'll see a dip, you'll see a peak, and it'll come back down again. Now, in order to see that peak and that dip between the two peaks, Dawes concluded that he needed to have a separation of what amounts to the full width at half maximum for the star. Rayleigh concluded that what you have to do in order to see the separation between two stars is take the 0 point of the second star and shift it over, so a little bit farther than what Dawes was saying, shift it over until it lines up with the peak of the first star. So there's the peak of the first star. You would shift this second star over until the first 0 of that star profile lines up with the peak, and then that's the Rayleigh limit. For our purposes, we're just going to talk in terms of the Dawes limit or in terms of full width at half maximum, recognizing that you could play games with whichever one of these that you want to go with. Dawes was working with photographic plates at his time. He had never heard of the word pixels. We have to deal with pixels. So if we actually want to see two separate stars, we've got to have a pixel showing us a bright spot, we've got to have a pixel showing us a dim middle spot, and we've got to have a pixel showing us the bright spot of the second star, which means our pixels have to be small enough to capture this separation. And this is where the Nyquist sampling theorem comes in. What Nyquist essentially said is that to resolve any periodic feature, whether it be a sound wave, a light wave, a spatial wave, as we're talking about here, in order to resolve a spatial feature, you've got to have two sampling points within that separation zone, which means the pixel scale has to be less than the full width at half maximum divided by 2 in order to see the Dawes limit resolution. And that's the Nyquist limit. We can never quite reach the theoretical Dawes or Rayleigh limits because telescope manufacturing quality affects things, the quality of glass. We live down at sea level. Our focus may not be ideal. And of course, there's seeing effects and guiding effects that ultimately combined all degrade the true and achievable resolving power of our telescopes. And now the question becomes, what can we do with the aperture and the Nyquist limit, pixel size, to get the best resolution out of our systems that we can? I'm going to talk about this issue in terms of my 4 telescopes. I've got a Redcat, William Optics Redcat 51, so it's 51 millimeters in diameter, a William Optics GT81, which has an 81 millimeter diameter, the Explorer Scientific ED102, and the Celestron C925, which has a 235 millimeter aperture. As we go down this list, we should be getting improved resolution because the aperture is going up in each case, and Dawes limit resolution improves with aperture. So my Redcat 51 has a Dawes limit, or full width at half maximum capability, given its diameter of 2.3 arc seconds. The GT81 is down at 1.4 arc seconds. The ED102 is at 1.1 arc seconds, and then, of course, as we just discussed, the C925 is the resolution powerhouse at 0.5 arc seconds. How well are these scopes actually performing? Here's a comparison of my 2 short focal length telescopes, the Redcat 51 on the left, the William Optics GT81 on the right. The green line represents the theory. That's the full width at half maximum. That's that formula I just showed you. I've also got these yellow plotting symbols. Now what they are, they correspond to the full width at half maximum as rated by PixInsight Subframe Selector for a series of blue images, oxygen 3, green, hydrogen alpha, S2, and red images that I've taken for a couple of targets for these 2 telescopes. I've got more data with the William Optics GT81 than the Redcat 51, so that's why there's some of these points missing over here for the Redcat. But this kind of gives you a sense of what I'm actually getting out of my telescopes versus what the theory says I should be getting. I don't expect to get what the theory says because there's all this other stuff going on. I'm living down at sea level. The focus may not be great. Seeing and guiding effects are certainly having an effect, and of course I have to deal with pixels that Dawes and Rayleigh didn't have to deal with. So I'm not expecting the yellow line to be on top of the green line. I just want it to be better. In case of the Redcat 51, the Dawes limit that I'm actually getting is about 4.83 arc seconds. But for the pixels that I'm using with this telescope, which are 3.8 micron pixels, the Nyquist limit says the best I can do is 6.27 arc seconds. So it doesn't even matter that this line is up here relative to the theory. It matters that my pixel size for this particular telescope is just too large. Now over here at the GT81, the story is very similar. The Dawes limit is 3.12 arc seconds. That's the average across here. So that's what I'm getting out of my GT81 at present. However, based on the 3.8 micron pixels that I have paired with this telescope, I'm truly only able to see resolution at 4.1 arc seconds based on the Nyquist limit. For these 2 telescopes, it's the Nyquist limit, the pixel size, that's controlling its performance right now rather than the actual full width at half maximum. So I'm not getting the most out of my aperture for these 2 telescopes. The ED102, I'm getting pretty good performance here, coming in around 2.4 arc seconds. And for the C925, I'm getting about 2.1 arc seconds for full width at half maximum. Now, the Dawes limit here is 2.42 based on my actual performance, and the Nyquist limit is 2.28 using the 3.8 micron pixel size. This telescope, this optical system, is actually operating at a near optimum condition based on the guiding and seeing and all those effects that push this yellow line above the theoretical green line. There's really not much I can do to improve the performance of the ED102. The Celestron C925 is supposed to be my resolution powerhouse, which is why this line is way down here at 0.5 arc seconds. But in fact, the performance I'm actually getting out of it is up here, and if you look at Dawes limit, it's 2.18 arc seconds based on what I'm actually getting out of the telescope. And the Nyquist limit is way down here at 0.68 arc seconds. For these 2 telescopes, the Dawes limit rather than the Nyquist limit, is actually controlling the resolution of these scopes. One of the most surprising things that comes out of this study is that my actual imaging performance in terms of full width at half maximum, Dawes limit, is actually about the same for these two telescopes. My ED102 is performing about as well as my C925. I'm giving up a lot of resolution performance out of my C925 because of guiding and seeing effects. How can we actually improve the performance of these scopes that I have? We've been talking about full width at half maximum, and I suppose there are three different versions of this number we could talk about. If we use the PixInsight subframe selector, it will go through the image and look at all the stars in the image and come up with an average, an image-wide average for a full width at half maximum, and that's 3.28 arc seconds for the image-wide average full width at half maximum. Now, I could also take the data from a single star, and that's what you see here with this blue line. So I've cut a cross-section through a single star in the image here, and I've fit a Moffat PSF star model to that. That's the orange curve, and it tells me that the full width at half maximum for this particular star is 3.12 arc seconds. But we don't really see either of those two numbers when we're looking at a particular location within an image. What we're seeing is a pixelated image where the pixel values are spread over the width of a pixel, and that's what you're seeing here. As we step up here, it gets brighter, each pixel gets brighter, but that brightness is constant across the width of a pixel. And so we could look at this image and say, well, there's our maximum, there's our half maximum, there is the full width at half maximum, and if you count, you have 1, 2, 3 pixels. Multiply the 3 pixels times the image scale of 1.12 arc seconds per pixel, and that gives you a 3.6 arc seconds for the full width at half maximum. This is what we actually see when we look at an image. If we're looking top down on an image, we see a bright spot, and we see a slight decrease in brightness on either side of that pixel, a fall off of even more brightness, and so on. Just for grins, let's take a look at the same picture for my SCT. It's obviously much more resolved because the pixel scale is much smaller, and you can see that the star model fits the actual star, in this case that I've selected. So the image wide full width at half maximum in this image is 2.63. This particular star is down at 2.01 arc seconds, and the observable full width at half maximum is 2.06. So because we have a much more resolved system here, the full width at half maximum as observed and pixelated is actually pretty darn close to what the Moffat star model full width at half maximum is. So in this case, you don't see the effects of the pixelation as much as you do with my other scopes. During an exposure, as we're making and sending guiding commands, that's basically taking the pixel array and sliding it back and forth under an otherwise fixed location for a star. Seeing, on the other hand, is atmospheric turbulence that takes the image of the star and moves it back and forth relative to a fixed pixel array. The net effect is a series of star images that are going back and forth across our pixel array and spreading light to adjacent pixels. And the extent of the motion of the star is represented in the guiding number that we see in the PhD2 guide graph. In other words, the total arc second RMS. That is telling us what the combined effect of the seeing and the guiding are. And after the exposure is done, what we find is that the ideal star profile that we started off with and should have based on the aperture of our telescope actually looks like this. It's much wider than the theoretical star shape because of the guiding and seeing effects causing the star to bloat out a bit. So what we want to do is to find the optimum pixel size for our telescopes given the kind of guiding and seeing effects that we have to deal with at our particular location. Here's an analysis that includes the effect of guiding with my Redcat 51 just as an example. Now down here on the bottom scale I've got the PhD2 total error. So this is this number here that we see in our guide graphs. I've got it plotted along here ranging from no seeing effects, no guiding problems at all, to very poor guiding, very poor seeing out here on the right end of the scale. For me and my EQ6R that I've been using, I've got a guiding performance that tends to be in the 0.3 arc seconds RMS on the low end, and if I'm lucky, 0.7 arc seconds RMS on the high end. Using my Redcat 51 with the 3.8 micron pixels, I'm getting fairly steady performance through here, which is what you want. You don't want the knee and the curve out here to be in here where your guiding is, because you'll be finding that you'll get some great pictures and some really poor pictures, and you'll have to throw out a lot of images. I don't know that I need to have this much headroom on guiding. This says that I could have guiding as bad as 2 arc seconds RMS before my images are affected with my Redcat 51. What I really want to do is to improve the resolution by bringing this line down, and then because I'm making this change, I'm also making my system more sensitive to guiding, and I want to bring that in up to the point where the knee and the curve is actually just outside of my guiding range. The only way to make this change is to reduce the pixel size. I will also getting an improvement in Nyquist resolution as well. I've been looking at the ASI 294 recently. I had not realized there was a one-to-one binning mode with the ASI 294mm. In the unlocked one-to-one mode, the pixel size for the ASI 294 is 2.315 microns, whereas the camera that I'm currently using, the ASI 1600, is 3.8 microns, and you can see this graph that I just showed you with the ASI 1600. If I were to instead replace the 1600 with the 294 in the unlocked 1x1 mode, I could do exactly what we were just talking about. I could improve the resolution in terms of full width and half maximum, and also in terms of the Nyquist limit, at the cost of getting a little bit more sensitivity to guiding performance, but still I'm quite comfortably outside my typical guiding performance, so this makes all the sense in the world for this particular telescope. Now, the Nyquist limit is still going to control here. The double stars that we were talking about before, they've got to be 3.8 arc seconds apart to resolve using a 2.31 micron pixel. The story is very similar for the GT81 as well. If I go from my ASI 1600, if I replace that camera with the ASI 294, then the knee and the curve comes in just at the upper end of my guiding, so this is about as good as it gets. Plus I get the benefit of a reduced full width at half maximum and reduced pixel size, and once again I will still be controlled in terms of resolution by the Nyquist limit, but now at least I've dropped it down to 2.5 arc seconds. Now, the Explorer Scientific is actually my best performing telescope and imaging system. The ASI 1600 with its 3.8 micron pixels, the knee and the curve is right at the upper end of my guiding. It's giving me the best full width at half maximum that I can have, and that happens to be on par with what the Nyquist limit is telling me I have based on the actual performance of the scope. But an interesting thing with the ASI 294 is that in 2x2 mode, you get a benefit of a 14-bit analog to digital converter as opposed to the 12-bit ADC that I have with the ASI 1600, which means it may be interesting to use the ASI 294 with this telescope, give up some resolution, but get tonal resolution that I can't get out of my 12-bit ADC of the 1600. In this case, the Nyquist limit tells us that the double stars must be 2.28 arc seconds apart to resolve the 3.8 micron pixels, and that's basically what I'm getting out of this telescope right now. The SCT is a complicated story. There are 3 lines here. Let's look at the yellow line first. That represents how I'm using the scope right now, which is no focal reducer, and I'm using my ASI 1600 in bin 1 mode. Now, you'll notice that I have potentially very good resolution down here, where more than half the light is concentrated in 1 pixel. However, I can't get down there because the guiding performance and seeing at my location doesn't let me get and make use of this very good resolution here. And in fact, even at the next tier of resolution with the ASI 1600, the knee and the curve is right in the middle of my guiding performance, so I'm not even going to get that consistently, and instead I'm going to be up here, which is where I am, around 2 arc seconds for this particular telescope and camera combination. The best combination for this telescope is to use the focal reducer combined with the ASI 1600 in bin 2 mode, and then that brings the resolution up to here, but it gives me a bit of protection against guiding and seeing errors because this curve is flat through here. And once again, it may be worthwhile taking a look at the ASI 294 in bin 2 mode, so I give up a little bit of resolution and I have a little bit more sensitivity to guiding that I don't have if I'm using the focal reducer reducer with the ASI 1600, but I get the benefit of the 14-bit ADC with the 294 that I don't have with the 1600. Now the story in terms of resolution is a complicated one. In the case of the using the focal reducer, the Nyquist limit controls and tells me the double stars must be 2.2 arc seconds apart in order to resolve them, whereas if I use the ASI 294 without the focal reducer, the double stars must be, surprise, surprise, 2.2 arc seconds apart in order to resolve them with the 2x2 pixels of the ASI 294. So in other words, I'm not doing anything to the resolution here. This is about what I'm getting right now. The one thing I would get with the focal reducer is reduced complexity in terms of focusing with the SCT and in terms of finding guide stars in the off-axis guider. Alternatively, using it with the ASI 294, I would get the benefit of improved tonal resolution as opposed to spatial resolution because of the 14-bit ADC. The theoretical resolving power of a telescope is governed by the aperture, and because we're astrophotographers, it's also governed by pixel size. So whichever number gives you the worst number is the one you have to go with. You need small enough pixels, according to Nyquist, to reach the diffraction limit of the telescope, which is governed by aperture. It's impossible to achieve the theoretical Dawes limit, or full width at half maximum, reported for telescopes near sea level. Thanks to seeing and pixel scale, my high-resolution SCT is performing no better than my ED102 refractor. Based on the analysis here and the actual performance of these telescopes, I'm seeing that a 2.3 micron pixel offered by the ASI 294 when paired with the Redcat 51 and GT81 scopes will provide improved resolution with no real increase in guiding and seeing sensitivity. It turns out that the 3.8 micron pixel size is just about perfect for the Explore Scientific ED102. I could give up some of the resolution by using the ASI 294 in bin 2 mode and get advantage of the 14-bit ADC, so I would have better tonal resolution at the cost perhaps of a little bit of spatial resolution. I think that's worth trying just to see what the trade-off is. SCT performance with the focal reducer and 2x2 binning is probably about as good as I'm going to get with my seeing here. I'm also interested in testing out the performance of my SCT with the focal reducer and 2x2 binning with the ASI 1600, and then comparing that to the performance I get with no focal reducer and the ASI 294 in 2x2 mode with the added tonal resolution provided by the 14-bit ADC. There is a reason to give serious thought to the ASI 294, whether in unlocked bin 1 mode or the standard bin 2 mode and the higher resolution of the ADC. I've ordered it. I've gone ahead and pulled the trigger on the ASI 294, and it should be arriving maybe tomorrow if I'm lucky. Okay guys, well thanks for sitting through this presentation a second time if you did that. Hope this one works for you. I'll talk to you later. See ya.